Good afternoon, everyone. So in the last class, we have seen that what are the differences between bit and qubit. Now, if we compare their time complexity, then you know the p problems and p problems, p space problems. So we'll get a diagram like this, or we'll get a figure like this. Now, if we try to just have a understanding about the power of quantum computing, problems that may take classical computers thousands years of time to solve, those problems quantum computer can solve within just seconds. Problems from the data encryptions, you have to know actually, quantum computing has an important application on data encryption. So this means to say that we maximum times use quantum computing for encryption purposes, means cryptography purposes. Then for some simulations were involving, like suppose inventing new drugs to create more precise climate model. So there are many areas where we can take the help of quantum computing. Now, why the quantum computing is so strong, or why the quantum computing is so fast? The main reasons behind them is these three terms, actually, three quantum computing terms behind this power. First one is superposition. Second one is entanglement. The third one is interference. Now, this superpositions, entanglements, interference, these terms I have already illustrated in the last lectures. Let's come to the new technical term, that is BQP. BQP stands for bounded error quantum polynomial time. Remember, BQP stands for bounded error quantum polynomial time. So in computational complexity theory, this BQP, that is bounded error quantum polynomial time, is the class of decision problems solvable by a quantum computer in polynomial time, with an error probability of at most 1/3 for all instances. I know that you already aware with the problems of decision problems, or non, means those problems which cannot be decidable. Now, it's suggested that it's recommended that the theory of computation paper, which is a basic paper that all CSIT students should cover, if you forgot those terms, kindly recall this term, read these terms again, that we have got in our theory of computation paper, like P complexity and P or P problems and P problems, then decision problems, problems which are not decidable. These terms you have to know, not just for this paper perspective, but you will find questions from those terms in your UC NET examination and GATE examination also. Okay, go through them. Even I will ask questions on them in the coming time. So please go through them. Now, this BQP is frequently related to these quantum computing based problems. BQP, again, I'm defining that this is the class of decision problems. Remember, what here said is decision. So those problems which can be decided, or which are decidable, right? Because some problems can be divided into two parts: those which are decidable, those which are not decidable. Now we are talking about that class of decision problems, with those problems which can be decidable and solvable by a quantum computing machine or device within polynomial time. Tumalke jana, you know that we have P problems and NP problems. P problems, polynomial time, computable or solvable problems, and P non-polynomial times. Now these problems are solvable in polynomial time. And error probability is at most 1/3. Okay, সবতকে বেশি 1/3 error probability হইতে ইয়াক quantum computer polynomial time solve কৰিব পাৰিলে if this problem, that particular problem can be solved by a quantum computer in polynomial time with maximum error probability of 1/3, then that is known as bounded error quantum polynomial time. Namtu ki ase? Bounded means there is a bound that 1/3 ke aru basic error nahe, right? Not more than 1/3. And quantum polynomial time, because this is solvable in polynomial time. A concept to the polynomial time and non-polynomial time bahute besi important hai, very important. So please go through them. Even in this paper also I may set questions from this polynomial time and non-polynomial time. At least 2-3 lines for this. Okay, go through that. It is so BQP, you got it. Hey bilak problem, Z bilak problem decide koribo pari, Z bilak problem quantum computer dara solve koribo pari, but kiman samoyot eta polynomial time samoyot mane eta infinite joage nai aru tar error probability at most kiman hobo paribo 1/3. Right? Okay. Now next, one more time we have got BPP. What is BPP? I hope that you got this term BQP. BQP bhalke buji pala. Now I am coming to the BPP. In computational complexity theory, bounded error probabilistic polynomial time, that is BPP, is the class of decision problems solvable by a probabilistic Turing machine in polynomial time with an error probability bounded away from 1/3 for all instances. That is not a different case, but only thing is that here we are comparing with respect to a Turing machine. And what type of Turing machine we are comparing here, or we are considering here? That is probabilistic Turing machine. Recall from our last lectures, you have got that what is Turing machine and what is charged means, or Turing thesis, you can say. These things we have discussed even in the first lecture. So BPP is the class of decision problem that will be solvable by a Turing machine. What type of Turing machine? A probabilistic one, and other parts is same, that is in polynomial time and error probability 1/3. Now, BPP is one of the largest practical classes of problems, meaning most problems of interest in BPP have efficient probabilistic algorithms that can be run quickly on real modern machines. It contains P, that is the class of problems solvable in polynomial time with a deterministic machine. And since a deterministic machine is a special class of probabilistic machine. So you guys have to remember that this BPP is the largest practical classes of problem. Kihor karone? Because it contains P. We try to avoid those non-polynomial time based problems, right? So B class is the maximum class, or most problems belongs to this. So BPP contains, as BPP contains P, so it is the case, or it is the class of problem which is the actually containing maximum practical instances of problems, and it is a deterministic one, so that's why it is again falling as a probabilistic Turing machine one. Because you know from our Turing machine classes that there we are talking about those problems which will be finitely which will be accepted in finite time, not infinite, in finite time, right? So a problem is in BPP if there is an algorithm for that, for it, that has some properties like it is allowed to flip coins and make random decisions. It can take decisions randomly, that it is guaranteed to run in polynomial time, and on any given run of the algorithm, it has a probability of at most 1 by t of giving the wrong answer. That is whether the answer is yes or no. So I'm repeating again, as it is very important. A problem is in BPP if some of properties will be satisfied. First, it can make a random decision. Second, guaranteed to solve in polynomial time or run in polynomial time. And for any run, the maximum probability for which wrong answer may come is 1 by 3. So we can say that a decision problem is a member of BQP if there exists a quantum algorithm, an algorithm which runs on a quantum computer, no doubt, that solves the decision problem with high probability and is guaranteed to run in polynomial time. A definition to monot rakhi loba. Remember this definition. Okay. A run of the algorithm will correctly solve the decision problem with a probability of at least 2 by 3. Okay, so today's question is this one. I have said that a run of this quantum algorithm will correctly solve the decision problem with a probability of at least 2 by 3. What does this line means to you? Why I'm referring here like at least 2 by 3 or at least 2 by 3 correct decisions. Analyze this line and you will show this answer to me in the next class. So as the topics are of high complex, so I recommend that you go through this lecture again. You'll get the recorded one, of course. Try to note down the terms that I have described, I have explained, and then answer the question in the next class. That's all for today. I'm stopping right here. Thank you.